Okay, so today is December 7th, 2011, lesson 6.7. We need to know our exponent rules to go through what we're doing today. So I have them up on the side. We did them much earlier in the chapter. We're dealing with an exponential equation. Y is equal to A times B to the power of X. A is the initial value, what we start with. B is our growth or decay factor. So if B is greater than 1, we're growing, we'll have an exponential model that'll head upwards. If B is between 0 and 1, we're going to have an exponential model that's coming downwards. We'll be decaying. And X is our exponent, usually the amount of time passing or the term in the question. Okay, so the first question reads, the population of Ontario was 9.3 million in 1985. So let's write that down. Ontario population in the year 1985. We'll write it up here. Try to make it organized like a chart. Our population was 9.3 million. Okay? And it says that it has been growing at an annual rate of 1.5%. Okay? This situation can be modeled by the equation P equals, so this is the equation they're giving us, and I'm going to show you how they derived it actually. P is equal to 9.4 times 1.0125 to the power of t. Okay? Where P is the million, where P million represents the population T after the year 1995. In which year did Ontario's population first exceed 10 million? Okay, so let's try to make sense of what we have here. We have this equation which is modeling our population growth. This is modeling the growth of our population. And they want to know what year T is going to be our years. They want to know when or in what year did the population finally cross the 10 million mark. Okay? So P is also the total population. We need to figure out when P is equal to 10 million. Okay? Now it's measured in the millions, they said P. So technically this number represents 10 for us. We're not going to write 10 million in for P, because P is measured in millions. So I'm going to replace the P in the equation with the number 10. So we get 10 is equal to 9.4 times 1.0125 to the power of t. We're trying to solve for t in this equation. We're going to be using a chart method to solve this. Okay? So first of all, I need to isolate for just my exponent with my base with the exponent variable. I want to isolate this part of the question. This says 9.4 times that. So I'm going to move 9.4 to the other side of the equation by dividing both sides of the equation by 9.4. On this side, the 9.4s will cancel out. And we'll be left with 1.0125 to the power of t. On the left side, we get 10 divided by 9.4. Can anyone read that? What's that say, Gio? 3 what? 8? Okay. So, from this point on, we're going to use a trial and error method to solve this. Okay? We're going to make a chart up, and we're going to plug in values of t to see when it will be equal to this value here. So I'm going to make up a chart. So we've made up a chart. We're going to be plugging in t values and finding out what their population is going to be equal to, or in this case, this is our p value. We need our answer to equal or get roughly as close as possible to 1.0638. So we have our calculator down here. Can I extend it? No, I cannot. Okay. We're going to be plugging these values in. So in our very first example, we'll do that in green. We have 1.0638 is equal to 1.0125. And I'm going to plug the number 1 in for t. So when t is 1, what does our right side of the equation equal? You know what? We're going to call this right side because technically it is in population, so I don't want to get you confused. This is the right side of the equation. 1.0125 to the power of 1 equals the exact same number. Okay? So we know it's definitely not after 1 year. We're going to do the same equation now. 1.0125, this time to the power of 2. Okay? Plug in our value 1.0125 to the power of 2 equals 1.025. So we're not quite there. And you keep moving up this chart. Next value, next question, 1.0125 to the power of 3. Equals, and when we plug it in, 1.0125 to the power of 3. What does that say? So we get 1.0379. That's our third value. So we would continue this pattern down. We're going to actually go through them just to make sure, because we're not that far, it looks like, from the answer. We'll do it to the power of 4. So now that you have this number in your calculator, you can just kind of follow along. 1.0125 to the power of 4 is going to equal 1.05. So we're getting closer to our value. And when we do the number 5 as a power, 1.0125 to the power of 5, 1.0, okay, this is important, 1.064, okay? So if we take a look at this, we have surpassed the number they were looking for. Okay? If we rounded, you're right, we would have ended up with the exact same number. So it looks like in year 5. Okay? Now normally though, because I haven't rounded this, I want you guys to actually make sense of this because population is something that's continuously growing. And what you're going to find is you're going to get two values. I'm going to bring them down right now. We'll circle them so you guys understand what I'm talking about here. We'll highlight them actually. So this value here and this value here. Now remember, we were just looking for that value because we needed it to be equal to this. What we found was in the year 4, our number was 1.05, it's technically 0.9. The value we were looking for was 1.0638. And then in year 5, we reached a population of 1.064. Okay? So in other words, we technically reached our 10 million mark between those 2 years. Years 4 and 5 is when we reached it. Now, from looking at these numbers, it's clear that it was much closer to the year 5. But if you run into a question like this, where the number you're looking for falls between the two of them, I want you to make sense of it and say between years 4 and 5, the population reached 10 million. Okay? Because technically in the year 5, it's already surpassed that amount. If we're looking for an exact amount, I want you to give me that little range, the range of a year in between. Okay, so what actually is very important about this is we discovered it was between 4 and 5 years from our initial value, which was in 1985. So what that means is we have to add 4 or 5 to 1985. Okay? Which means it's going to take us to between the years 89 and 1990. That, between those 2 years is when the population reaches 10 million. Okay? Because recall that our starting date was in the year 1985. Example 2. Caffeine has a half-life of approximately 5 hours. Okay? Anytime we're doing a word problem, make sure you write down whatever information they're going to give you. So, they said that caffeine has a half-life of 5 hours. That means, yeah, we're going to have exponential decay. Caffeine half-life is 5 hours. Let's extend this a little. There we go. Now, what that means is, if you guys remember from our variables above, that means our H is our half-life. Yeah, it's going to be the number 5. Suppose you drink a cup of coffee that contains 200 milligrams of caffeine. So the initial value is 200 milligrams. That means we're using our A at O. Yep. So H is 5. Our initial value is 200 milligrams. How long will it take until there is less than 10 milligrams of caffeine left in your bloodstream? So they're talking for the amount after a time. That is our A value. They said they want to know when the A value, how much time will it take for the A value to decrease to 10 milligrams. So we're using exponential decay, which is this formula here. Oh, I did that in green, not blue. My fault. Try to get the colors the same. So our new amount is A, and we're going to be looking for T. They're asking us for how long it will take. So we're solving for our T variable. So our equation reads, our new amount is going to be equal to the initial amount multiplied by 0.5 to the power of T, that's time, divided by H. We're going to put our values in. That's a question mark. Our A is going to be 10. We'll do them in the colors, actually. So we have our 10 is equal to the initial value. The initial value is 200 multiplied by 0.5. Our half-life was 5, and we're still looking for our T. So we have to use the same idea in order to solve. We're going to have to use a method of trial and error. So, like before, we want to try to make this side of the equation as simple as possible. So, think of this as a term multiplied by 200. I'm going to move 200 to the other side of the equation, so we're just working with that term. We'll have less to punch into the calculator that way. So when I move 200 over, I'm going to get 10 divided by 200 is equal to 0.5 to the power of T divided by 5. Divided by 200, 0.05 is equal to 0.5 to the power of T divided by 5. So this is where we make our chart again. Just use lines this time. We're going to plug in T values. and we're going to be looking for a number that is equal to 0.05. We're trying to equal that. We need t to equal this amount. So what we're going to do is going to plug these in. Now in your calculator, you're going to have to divide your exponents first, figure out what they equal, and then put it to the exponent of 0.5. So what I mean by that, for instance, for the number 1, I would do 1 divided by 5 gives me 0.2. So 0.2 is my exponent. I then put it to this base of 0.5. So I have 0.5 to the exponent of 0.2 equals. I'm going to do this along in my calculator at the same time. So for our number 1, when t was 1, we got the value of 0.87. Not quite what we're looking for. In fact, it's a good ways off of what we're looking for. Alright, so our next value, exact same idea. This time we start with the t value of 2. So we have 2 divided by 5, 0.4. So I'm going to put 0.5 to the power of 0.4, 0.5 to the power of 0.4, 0.75. Okay? So we're slowly getting closer and closer to this value. But we're still a ways off. So what I'm going to do in terms of time's sake is we're going to try to skip a few and see how far we get. We're going to jump down to 5. 5 divided by 5 will be 1. Okay, that's a good point. 0.5 to the power of 1 is still just going to be 0.5. We're not close enough yet. Okay, this is a good way to cut off time on your test. I'm still not nearly close to 0.05 because I am decreasing. So let's jump again to 10. Let's see how this goes. I'm just going to extend the line a little. So when we put 10 in, 10 divided by 5 will give us the value of 2. So 0.5 to the power of 2, 0.25. Guys, notice a little pattern here? Almost splitting in half here as we went from 5 to 10. Want to go 20? Sure.
Go to 1,000.
Let's try 20. 20 divided by 5 gives us 4. 0.5 to the power of 4 equals. Oh, we're getting close. 0.0625. All right. Now, because we've jumped quite a bit. If I had actually put in all the values of 20, this would have took me a very long time to do. We jumped. We're getting close. We're looking for 0.05. We're at 0.06. So I'm going to start to slow down a little. Okay? I don't want to jump too far. So I'm going to jump up to 22. See where that takes us. 22 divided by 5. So 0.5 to the power of 4.4. Okay? 0.5 to the power of 4.4 gives us 0.047. 0.047. We're too low. So we're going to check 21. Okay? Because we've gone below what we were looking for, we're going to check the number 21, which is the one in between. 21 divided by 5, 4.2. So we get 0.5 to the power 0.54. Okay, so this is what I was talking about before, 0.054. If you guys notice, the value we were looking for, which was 0.05, okay, is in between those two numbers. So in other words, our time is in between 21 and 22. So time in this question was measured in hours. Okay? So because time was measured in hours, what we're looking for is between 21 and 22 hours. Between 21 and 22 hours, caffeine, caffeine, reaches 10 milligrams.
So does that have to be 0.05 rounded?
Well, I want you to try to be as exact as possible.
What if it's like
Homework, page 391, 1, 3, 8, 11, and 17. Try those questions.